Hey there, Math 124 fans. In this first part of this Exam 2 review, I'm just going to talk about derivatives and tangent lines. I'm not going to make this part very long, but I will point you to some other resources. At this point, if you're given a collection of terms, maybe before we do this example, let's start more basic. If you're given a sum or difference of a bunch of different things, at this point, hopefully you have started to collect your thinking. And what I mean by that is the following. I'm just making some things up as we go. So hopefully at this point, you know how to attack that. So if somebody said, take the derivative of this thing, you would think there are three separate terms. And by term, I'm saying something that's completely separated by a plus or minus. Here, let's make this a minus. That means there are three different jobs to do. We say the sums and coefficients come along for the ride, or I say that. Those are the sum and coefficient rules. Okay, once you're done with that piece, then you see you have separate jobs, three different terms. And for each term, you're going to ask yourself, is it something we already know how to do? Yes. Is it something that's a mess? Yes. Then we think, is it a product rule, a quotient rule, or a chain rule? And here you would say product rule and start using the product rule. Here you would say chain rule and start doing the chain rule. So that's the overarching, like if you just have a function of x, how you take the derivative. There's the quick version of that. So let's now look at this example I have over here. It's just one term. So I wanted to say that as a warm-up. So it's just one term. So this one's about, do you know what that's saying? And really the challenge isn't a calculus challenge. The challenge is just, do you know how to read a function? Which is an important skill in and of itself. Okay, so what does all that mean? Let's write it down the way a calculus student might want to think about it, which is, what does this mean? And you've been practicing the homework, but you'd have to know that this means this. That little dumb notation there means this. It's not a bad notation, but it adds confusion, so you have to understand from your practice. Okay, so we have a big thing all trapped in a fifth power. You have a technique for that. So for these ones where you have a bunch of stuff trapped inside of something else, it's a chain rule question. You can pretend you're walking up to the function. The first thing you encounter is this parenthesis. What is it attached to? This. You should at some point be able to just see that all of this is inside a fifth power function. The chain rule says to take the derivative of the outside. So it's 5 to the 4. Done. Then you erase. Now eventually you don't want to have to actually erase. You need to just be able to do these things. You keep walking. The next thing you encounter is this t. It's this function that's on the outside, tangent. Now the main thing you have to remember about the chain rule is the inside does not change. And then you do times, and then you have a new problem. It's times the derivative of tangent. You need to remember that that's secant squared. Then we're done with that part. Keep walking. Next thing you encounter is e. This is trapped inside of e. Leave the inside alone, and then do times the derivative of the inside. Now the derivative of e to the blah is e to the blah. And we keep going. So this is a real big chain rule problem. We leave the inside alone, times the derivative of the inside, which is 3. Done. Now once you get good at this, you should just put these together. I had a student in my business math class tell me that they asked me if they could use the telephone method. I had never heard anyone call this. It's just rearranging multiplication, then that's 15. Yes, you can use the telephone method. I just thought it was funny. I'd never heard anybody say that. Okay, that's it. So that's kind of the basics 101 of derivatives. Shouldn't be scared by a chain rule question. Okay, let's grab another one. And I'll finish this up by sort of showing you where you could find plenty more practice. So what does this one say? Here's a function. It's arctangent. Now arctangent is sometimes, and I tell students x over 2 is the same as 1/2 times x. You need to be comfortable as a calculus student being able to rewrite things. This is the same as arctangent. That does not mean the negative first power. It means arctangent. So we need to know those derivatives. This would be derivatives you should know. So as soon as it says slope of tangent line, I start taking the derivative. G prime of x is 1/2 plus, and then the same thing. I need the derivative of arctangent. Now the derivative of arctangent of blah, I sometimes put blah just to emphasize it does not matter what's there. It's some function of x. So a good mathematician, which is not me, would write f of x and say, okay, whatever that is going to be 1 plus f of x quantity squared times the derivative of the inside. So this is going to be 1 over, this is the weirdest, one of the weirder derivative rules you encounter. So it looks funny to people, so it's harder for them to do what I just did the first few times. But then you say, okay, you erase that, you put in a 2x, and then you do times the derivative of the inside, which is 2. And at some point, the more and more you do these things, you're going to get to where you really need to be able to simplify as you go, because if you have to redo every little thing, it's going to get pretty bad, and it's going to take forever. Let's find the values at which the slope is 1. So when is this equal to 1? Oh, we have a little algebra exercise. This is a good example of a situation where it looks bad only because there's fractions. So I often tell students, well, in this case, I'm kind of inclined to subtract the 1/2 from both sides. But that's not the reason it looks bad. 1 minus 1/2 is 1/2. I think a lot of students tell me to cross multiply, which is fine, but really the key idea is you're clearing the denominator. So the truth is, cross multiplying is not necessarily how I think about it. I think about multiplying both sides by the denominators to get rid of the denominators. So you get 4 is equal to 1 plus 4x squared. And then we got it. 3 is equal to 4x squared. X squared is 3/4. X is plus or minus the square root of 3/4. Oh, and I forgot that I was going to try in this video to have my solutions open. I hate looking at solutions. I didn't want to model what my students should do, but I know I'm making a video, and if I make a video, I better have something right. Okay, let's do another one here. Here we go. Find the value of x at which this has a horizontal tangent line. So another derivative question. Here's an opportunity for us to talk about how does a calculus student think of a square root? And you may eventually get to where you know this rule and can do it in one step, but until we're there, here's what you do. That's the way a calculus student thinks of a square root. It's uglier. Calculus students tend to look at things in ugly ways so they can use their derivative rules. The derivative of the outside is this. And as I said, this needs to become second nature if you're going to continue in any calculus class. Then you take the inside, leave it alone, times the derivative of the inside. 4 minus 4/3 x to the 1/3. How did I do that? Well, I've practiced with fractions enough to be comfortable doing that. The question is asking when it has horizontal tangent lines, so it's asking when this is 0. And this is a good opportunity for me to talk about this other idea, which is fractional exponents, negative exponents. Those are good for calculus. They're sort of bad for solving. So to me, the moment I get to a point where I'm starting to solve, I get rid of those negative exponents. How do I do that? I'm just going to rewrite this as 1/2. With practice, you can do this in one step. 4x minus x to the 4/3 to the 1/2. But at this point, maybe I'll rewrite it as a square root. I'm done making it look ugly. Times this thing. But for me, I'd rather put that on top. And it's amazing these little things, sort of understanding, are we trying to do calculus or are we trying to do algebra? If we're trying to do algebra, we should write it in a nicer way. I find when I write it that way, it's even more clear what needs to happen. If you don't write it this way, I find that students sometimes set this equal to 0, which doesn't make sense, because if the denominator is 0, none of this makes sense. When you set this equal to 0, the only way this could happen is if that numerator is equal to 0, and that might have been hard to see if you were writing it in the calculator, the calculus form, so to speak. And that's my own language for this, but I think it's an important understanding of what are you trying to do. You should set up your work in a way that naturally allows you to do what you want to do. And this negative exponent is not easy to work with when you're solving. The only reason we did it was because we were doing calculus, so that we could use our rules. Okay, so I'm going to divide both sides by 4. That gives me 1. Then multiplies both sides by 3. I get to the 1/3. Now, if I remember correctly, a lot of students get this wrong. They do cube root. If you're trying to get rid of a cube root, you cube both sides. So you get 3 cubed. It's 27. So to me, those questions are somewhat tame, but usually there's some of that on any exam relating to these topics. I hope it's coming along. So I found one more. Sorry, for some reason the screenshot didn't come out very nice. But here you go. There is a plus here, but it's trapped inside of a 10th power. And so my function looks like this. So the derivative is going to look like this. It's a chain rule problem. The chain rule is by far the most important rule we use a lot in combination with the other rules. A calculus student might want to rewrite this as sine of x quantity squared so that you can clearly see what's on the outside. Okay, so this doesn't change. I'm going to write it pretty again over here. I'm going to do dot. I'm going to put parentheses, and whatever the derivative of this is, I'm going to put it there. Now, there are now 2 jobs, and sometimes people get this part wrong. They'll forget these parentheses, and they'll just start doing the derivative of each one. They'll do 2 sine of x to the 1, which is the derivative of the square, and they'll do this. I've just seen this a lot. And somehow this gets completely detached from the rest of the problem. So that's why I was saying about those parentheses. All of this needs to be attached. Don't let that function escape. Okay, then you need to do, so I did the derivative of the 2 times the derivative of the inside, which is cosine. Does the cosine go out here or go out here? Well, the cosine's only part of this derivative. Then it's plus, and then I use the derivative of that, which is going to be, I'm going to write it in front here, 20x to the 3rd. So with practice, this becomes more and more tame to do. It's something you need to practice if you're going to continue on into the other calculus courses. So briefly, I do have a page here that's just derivative practice. Now, some of these are ones that require other stuff, like logarithmic differentiation, but hopefully you can see question 1, you can do it right away. 3 log of x is quantity squared times 1 over x. Hopefully you can do this one right away. Secant squared e to the x times e to the x. Oh, this is just a goofy one. I'm sure it's 0. This is to see if the 7 bothers you. So I made this sheet up years ago. There's a quotient rule. There's a chain rule. This doesn't scare me. It's a product rule. There's a few of those that more stuff is needed. You need to be really comfortable with that, not just for your test, but just moving forward. Okay, so I think I'll move beyond that and move on to the next video, but I hope that was helpful.